Welcome everyone to the webinar series. I'm Anand Patil. I'm the director at Bridge Software Institute. Firstly, I want to make sure everyone can hear me. Could you just raise hand? Uh, okay, nice. I can see some raised hands there. Awesome. So everyone can hear me. Uh, Today is the first of the webinar series here, creating peer models in FB-MultiPier. And Clinton Munari, he will be presenting. We have other two webinars that in this series. One is in October 8th, on October 8th, creating bridge models in FB-MultiPier. And the last one is on January 21st, advantages of using bridge models. We would, as time goes, we would add on to this series or make a new series depending on feedbacks from the clients and how this series goes. Please register using the link that you see there, bsi.ce.ufl.edu/webinars. So before starting, I just wanted to thank everyone to take time out of your schedule and to come to the attendance here today. We understand that your time is valuable and we want to make the best use of your time today. As far as the goals go, Clint, can you go to the next page? As far as the one back. Yeah, as far as the goals for today, we want to make sure we help you with better understanding how FB-MultiPier program operates, training on the effective use of the program, and demonstrating step by step how to create a peer model in FB-MultiPier. As far as the agenda goes, the first one will be just a brief introduction here and followed by the actual webinar content. And the last 10 minutes is reserved for Q&A and discussion. So if just want to make sure everyone is muted during the webinar, and please use the Q&A panel on the Zoom to ask any question during the webinar. And if you want to, so Wilmer and I will keep on answering those questions during the webinar. But if you want to ask a direct question, you have to wait till the end of the session, last 10 minutes here. And during that time, you can raise your hand and we can unmute you and you can ask your question directly if that's what you prefer. If we cannot get to all the questions today, we would definitely reach out to you via email or a phone call to make sure we answer all the questions that comes today. So lastly, we are recording this webinar as well. And without further ado, let's get started with the webinar. Clint, can you take over?
Okay, thanks, Anand. This webinar is called Creating Peer Models in FB-MultiPier. As Anand said, my name is Clint Minari. I work at the Bridge Software Institute on various interfaces for our software, including FB-MultiPier. So goals for this particular session, we're going to be creating a peer model in MultiPier starting with our default model. And we're going to showcase some of the features. And there will be a lot of overlap in what we look at today, even though we're focusing on a peer model. There'll be a lot of overlap between what we do with this model, a peer model, and other models that we have in MultiPier, because MultiPier also can do pile bands, retaining walls, sound walls, bridges, etc. So you're getting a lot of bang for your buck here, hopefully, today. Okay, so we're going to transition specifically as we work through MultiPier with a peer model today of taking the default peer, which looks like this on the left-hand side of this slide. And we're going to use that default peer and build it up to model a pier that exists in the Melbourne Causeway. Melbourne Causeway is just about at the end of the 192 roadway in Central Florida. It terminates in Brevard County in Melbourne Beach and in the Atlantic. So the particular pier of interest that we're going to work on today is the first pier in the eastbound side of the causeway. So in this image here, we're looking east, and it's the closest pier in the image. And Indialantic is on the left in the distance, and the Barrier Island and Melbourne Beach is on the right. So that's our pier. The things, some characteristics that make this pier a good candidate for the demonstration of a bunch of the features in multi-pier today. 6 bearing rows in 6 bearings in each row. There's 2 rows of bearings. We have tapered cantilevers. We have circular columns, 2 of them. We have an extra member laid across the pile cap at the base of the 2 columns. And then we also have essentially 2 platforms with a gap in the middle where the water can flow through. And so we're going to remove shell elements in multi-pier to achieve that. So those are the major areas of modeling that we're going to focus on during this particular demonstration. So in multi-pier, if you've already created an input file and saved it, of course, you can reopen that model and continue to build it up or do whatever you want. But if you're starting fresh, you always start with a default model. And since we're doing a pier model today, we're going to start with the default pier model in multi-pier. And to do that, you click on the File menu or the File button under the File menu and select Pier. As I mentioned, there's several other model types. You can see them here, but we're going to focus on the pier model. So we're going to go ahead and bring in the multi-pier program now, and we'll go through step by step what's necessary to take the default pier model and use it to ultimately model that eastbound pier in the Melbourne Causeway. So we'll come up here to the File menu, and we'll go New, and here's our pier selection. And we can see that the interface is now populated both in the graphics windows and also the data window in the top left, which is the model data window. And these windows are quite interactive. You can zoom, pan the model. Also, there's right-clicking will give you access to a lot of features on the context menus. First thing we want to do, first thing you should always do when you open a default model in multi-pier is assign a name to it so that you got a place to store it. So we'll call this Melbourne Causeway Pier. We'll put today's date on there. Okay, so now we've got a place to save our changes. It's certainly a good idea, just like with any software, to save your model on a regular basis. I like to do it really each time I make a major change to the model, and we'll be making several major changes as I just laid out and looking at the pier characteristics a minute ago. So definitely want to save the model on a regular basis. We're going to start by navigating to the pile cap, because recall in looking at that pier, essentially you have 2 platforms and then water running between them. So we'll come to the pile cap page, and we're going to set the number of grid points, and that'll give us as discrete a grillage as we want. In particular, we're going to set the XP number of grid points to 34. Program's going to prompt us, and it's just reminding us, hey, you've done something to your pile grid. You might want to look at your P multipliers. We're just going to click OK to that. We're not going to get into P multipliers in this demonstration, but that's just the program warning us. You can see that in real time, the graphics windows of the program immediately updated to reflect the fact that we now have 34 grid points in the XP direction. We need to modify the YP grid points also. So by default, that was 7. We're going to make that 17. And again, same message, P multiplier warning, which we're just going to click OK to. Okay, so we've got a much larger pile cap than we started with, and we have several things that we need to do to it. Multi-pier is pretty flexible. You can do a lot of things in different orders, but the way multi-pier was set up, we think is hopefully an intuitive order as far as marching through the pages from top down to do the things that you need to do to build up your model. So we're in the substructure section here on the pile cap page, and we're going to go into the grid spacing table. We have the number of grid points we want now in the X direction, the XP direction, or the YP direction. But now we have to go in and specifically alter the spacings between those grid points to get the pile cap ultimately of the size that we want. And so almost all the grid points in the XP direction, almost all, but not all of them, are going to be 12 inches, 1 foot. So we want variable spacing, but because we know that almost all of the spacings are going to be 12 inches, 1 foot apiece, I'm going to use constant to save us some typing and save us some time. So I'm going to input 12 inches. I'm going to click update. That's going to assign 12 inches. You can see the grid updated. That's assigning 12 inches to every single spacing in the XP direction. Then I'm going to switch back to variable, and I'm just going to do a little pruning here, and I'm going to update the very few number of spacings that we don't want to be 12 inches. There's a few spacings we want to be 9 inches. That's going to be spacing 1, spacing 16, spacing 18, and the last spacing in the XP direction, which is spacing 33. Okay, so that was a lot quicker than if I had to manually come in here and go 12, 12, 12, 12, 12, 12, 12, 12. There's one other spacing we need to change, which is this guy in the middle, and we're going to use the dimension of 198 inches there, and that's going to help us remove one nice big swath of the pile cap when we remove some shell elements in a little while. So we have that gap between the two parts of the pile cap. So that's our XP spacing. While we're on the dialog, we're going to do something similar to the YP spacings. Now, most of the YP spacings are also the same, being 12 inches. So I'm going to do the same thing here. Input a 12. When I click update, that's going to assign 12 inches or 1 foot for every single YP spacing. I'm going to switch back to variable. And then there's a couple spacings in the YP space out of the YP spacings that are not 12 inches. And those two are the first and last. So that's spacing 1 and spacing 16. Okay. So we've got our spacing data input. I'm going to click OK. And then our graphics window is going to update. And you can see here that, yeah, we've now got a pile cap that if you imagine removing the shell elements in the middle here, would pretty closely approximate that Melbourne Causeway Pier. I'm going to go ahead and save the model. Like I mentioned, we made some major changes to the model already to the grillage, so we're going to save it. Next thing we're going to do is we're going to modify the pile cap thickness. Right now, the thickness by default in the Pier model is 5.5 feet. So that's the vertical dimension here. I'm going to change that to 5 feet. Okay, just a little minor update. You can see that graphically. And then I'm going to come over here to the pile plan view and make use of the context menu. Like I mentioned before, there's a lot of functionality there to position the piles at the precise grid locations that we want. So I'm zooming in the model right now, so you get a nice look at it. That'll make the grid points a little bit bigger physically, which will make them a little easier to click on. I'm going to right click to launch that context menu. And I'm going to choose add remove piles. Okay, and then when I choose add remove piles, that's going to put me in a mode where whatever grid point I click on, it's going to position a pile there. So I'm going to click on a grid point right here, and now we've got a pile. And we want, for this particular pier, we want 4 feet in between each pile face. And we know that most of these grid points are a foot apart, other than the ones that are pretty obvious. There's some 9 inchers here at the edge, and then there's this one big one in the middle, but we can count 1, 2, 3, 4. So this would give us 4 feet, right? I'm just counting the spacings here, 1, 2, 3, 4. Then we're going to want another 4-foot gap here, 2, 3, 4, 1, 2, 3, 4. So we're going to put one right here, okay? And then we're going to repeat that. So we want 4-foot spacings all the way across the top part of this cap. And then we're going to duplicate the same thing on the bottom part of the cap. So all I'm doing now, that because I'm in add remove piles mode, is clicking on grid points. And when I click on one, if there's not a pile there, a pile will be placed there. If there is a pile there, the pile will be removed. So we're going to mimic what we did up here down below. Again, we want 4 feet in between each pile face. Okay. 1, 2, 3, 4. Whoops. Okay, right here. And remember I said if there is a pile present, clicking on a pile in this mode will remove it. So I'm going to click on, this is where the piles, due to the original pile cap geometry and number of grid points, when we expanded the number of grid points out, the piles relative to the much larger pile grid that has many more grid points, the piles essentially are down in the bottom left-hand corner. So we're going to click on them to remove them. We had 9 piles to start, so there's going to be 9 piles down here in this corner. Okay, so now they're gone, but now we want to complete this row here. Okay, all right, so we've got 2 sets of 9 piles. I'm going to go ahead and save the model. Okay, and let's take a look at the model in the 3D window. And that's looking pretty good. That's looking pretty good. But recall, we need to remove the shell elements in the middle here. So that's another function that's available in the pile plan view. So we're going to right click, and there's a couple different ways we could remove it. We're going to use a drag box rather than just have to pick the individual shell elements. We'll use the drag box to remove the cap. So I'm going to select that from the context menu, remove cap drag box. And then I'm going to hold down the left button of the mouse, and I'm going to drag a box over the shell elements that we want to get rid of. Okay. And then I release the left button of the mouse. And that removed those shell elements. So now if we take a look at our model here, right, that's what we want there. We want water in between the 2 parts of the pile cap. So that was another major change. We'll go ahead and save the model. We're going to go to the soil page now. This particular demonstration is not going to be particularly soil intensive, but we do want to do a couple things on the soil page. So soil page is another page in the model data property window. We'll click that. We want the water at sea level. So I'm going to change the default -10 feet to 0 feet. And you can see the 3D window updated, and it put the water table elevation at the midplane of the pile cap. And then we're going to change the top of the soil from -30 to -10. The Indian River Lagoon is the waterway that on which the Melbourne Causeway Pier sits. And if you guys are familiar with that waterway down there, it's quite shallow. I'm not sure what it is in the channel in the middle, but it's quite shallow. So we'll do 10 feet for the top of the soil. Now we can take a look in the soil edit window and see the same type of thing that we're seeing over here in the 3D view. We've got our water table elevation right there at 0. We have our soil here at 10 feet. We have a elevation bar that's helpful in the soil edit window, where if you drag your cursor, it'll let you know exactly where you are relative to, it'll let you know the elevation that you're at. That can be helpful if you're trying to look at where a layer change that you created is, or get feedback on where a particular node is relative to a layer change. So next thing we're going to do is the structure. We know from our original model that we want 1 column residing on each section of the pile cap. So that's definitely something we're going to need to take care of. So we'll come over here to the Pier page. And on the Pier page, we'll start modifying the structural data. That's the pier cap, the columns, and then ultimately the cantilever. So the first thing we're going to do is increase the pier height from a default of 18 to 26. See, our pier just got a little bit taller. The cantilever lengths are uniform. We're going to make them 10.5 feet each. Okay. Column offset. Column offset is the distance from the edge of the pile cap to the center line of column 1. And by default, that was 3. We're going to set that to 7 3/4 feet, 775. Okay. And we're also going to set the number of column nodes. I'm going to go into thin. Actually, I'll use overlay mode here so you can see the nodes inside the thick model. So the column node input, that's how you specify how many nodes you want between the column base, which is where the pile cap is, and the column top. So right now, 1, 2, 3, 4, 5. Right now we have 5. We're going to change that to 25. You can see that didn't change the length of the column or the height of the column, but it greatly increased the number of elements along the column. That's going to be handy a little bit later when we want to put an extra member in at the base of the columns at a precise location, so we can get that extra member's bottom really nice and flush against the top of the pile cap. Okay, so we've got our 2 columns, we've got our column nodes where we want it, and we have our cantilever lengths, but we need to increase the spacing between these 2 columns so that one column is sitting in the middle of this pile cap section, and this column, column 2, is sitting in the middle of this pile cap section. So we're going to come over here to column spacing, and that's going to launch the column spacing dialog. And we're going to input a column spacing of 32 feet. Okay. Okay. And 32 feet shifted that column to where it's now positioned in the middle of this pile cap section. So that is what we want. Taking a look at our model, we can see like, yeah, this is starting to take some shape here. It's starting to bear some resemblance to the Melbourne Causeway Pier. We certainly have some dimensions of the column and pier cap that we need to address. It's a bit skinny right now, so we're going to thicken that stuff up, and we still have that extra member that we need to lay down. And we also have the bearings to address. So we'll tackle the bearings first. So by default, the Pier model has 2 bearings. We are going to adjust the bearing configuration as the next step. So from the Pier page, I'm going to click the bearing locations button, and that launches the bearing locations dialog. So there's a bunch of input that we need to do in this dialog. Fortunately, the left row and right row are mirror images of one another. So we can duplicate the input. Once we get it in for the left row, we can do the same thing in the right row, and that'll be nice and efficient to do that. So first thing is we're going to want variable bearing spacing. That's the distance, the spacing between each pair of bearings. So we don't want uniform. We want to be able to customize the distance between each pair of bearings. So we'll go to variable bearing layout. By default, there's 1 row. We're going to want 2 rows. And then recall we need 6 bearings in each row. So we'll do 6 in the left row, 6 in the right row. We're going to need to input the column offset. And this is the distance from column 1 to the first bearing. And so we actually want the first bearing to be positioned to this side of the first column. So that's going to be a negative value. That's going to be a value of -8. The drawing's not updating yet because we're in a modal sub dialog here, but it'll update after we get all the bearing information input and we click OK. So we'll want -8 for both those, for both column offsets. And then we're going to want the bearing offset, which is the distance from a bearing row to the center line of the pier cap. We're going to want those offset from the center line 1.5 feet. Okay. And now the spacings themselves, recall we chose variable spacing. So we're going to input a set of spacings in the left row, and then we're going to duplicate it in the right row. So we want 9.25, 10 feet. This is in feet, by the way. 10 feet, 9.5, and 9.25. And we want the same thing in the right row that we have in the left row. So I'm just going to double check our input here, make sure we're matching 6 and 6, -8, -8, 1, 5, 1, 5. We'll leave the tolerance alone for the bearing node merging. We've got variable, 2 rows, match, match, match. Great. So now when I click OK, the drawing windows in the program are going to update. And there we go. Now we've got the position and number of our bearings the way that we want it. They are hanging a little bit off the edge of the pile cap, but that's not an issue with the bearing offset that we chose. That's just a function of we haven't got around to widening out the pier cap or the columns for that matter. But the bearings are physically in the position where we want them to be. So I'm going to go ahead and save the model again. And now we're going to get into modifying some of the cross-section data for the columns, the pier cap, and the cantilevers. So to do that, our launching pad is going to be the pier page, and we're going to click the edit button. Okay. And the top left corner of the dialog that just popped up, this is a suite of dialogues to modify cross-section data for the columns, pier cap, and extra members. Then the top left corner, that is where you select the component that you want to modify, right, for which you want to modify cross-section data. So we want column, that's the first thing we're going to tackle. So column selected by default. We're going to change the shape because these are circular columns in this Melbourne Causeway pier. So we'll go with circular. You can see the graphic updated. And then the diameter is 60 inches. So we're going to modify that. Okay. All right, so we have the right dimensions. And again, the graphics windows are going to update after we click OK on the modal dialog. But while we're in here, we want to not only affect the dimensional input for the column, but we also want to go ahead and input the steel reinforcement. So I clicked edit cross section. Now this gets us down into our steel reinforcement dialog. And there's a couple different methods you can use to input steel reinforcement in a cross section of MultiPier. For the column, we're going to use a percentage method. So that radio button is right here. And it's going to ask me for a few pieces of information. I'm going to input the cover thickness of 5 inches. And I'm going to input a minimum spacing of a small value. I'm just going to put in 0.1 inches. And then I'm going to click generate layout. When I do that, the program is going to offer me a bunch of options based on the bar number. It's going to tell us how many bars would be in that bar group, and then what percentage of the cross section would consist of steel reinforcement. So we're going to go with the number 8 bar. We're going to click OK. And when we do that, we can see that our cross section drawing updated to show the appropriately placed circular bar group. So I'm going to click OK. I'm going to click OK. And now we can see in the 3D model, we have circular columns, which is what we want. And we've put rebar in there in the same breath. I'm going to go ahead and save the model. Okay, so the next cross section we're going to tackle is going to be the cross section for the pier cap. So I'm going to dive down into the cross section suite of dialogues. And I'm going to do that by clicking the edit button. And again, top left of the first dialog, the full cross-section pier component properties dialog, that's where I select the component that I want to modify. So I'm going to select pier cap. And we do want a rectangular pier cap, but we're going to want to increase the dimensions, and we're also going to want to modify the rebar. So we'll leave the section type as rectangular, but we want the width and the depth to be 6 feet, so 72 inches for the width and the depth. And then similar to what we did for the column a minute ago, we're going to use the percentage method to input steel reinforcement. So I clicked edit section contents. That launches the rectangular section properties dialog. And once again, we're going to choose percentage. And this time it's not a circular section, it's rectangular. So we're going to input a cover thickness in both the 2 direction and the 3 direction. So in this case, we're going to want to put 4.5 inches for our cover in the 2, 4.5 inches for our cover in the 3, and then I'm just going to put a small minimum spacing there, and then I'm going to click generate layout. Okay. Once again, we're going to choose the number 8 bar. That has 40, choosing that option, that's going to consist of 40 bars. And we'll click OK. And you can see it looks like more than 40. Hold on a second here. I didn't choose 8. That was more than 40. Okay. Now I chose the number 8 bar group. That's 40 bars. We're going to click OK, and we're going to come all the way out. And now we can see that our pier cap dimensions are much thicker than they are before. And remember the way we had set up the bearing offset, when we still had a skinny pier cap, the bearings were hanging off of the edge. Well, now we've widened out the pier cap to the dimension that we want, and our bearings are now, there's enough real estate for them to comfortably sit on top of the pier cap. All right, so we're going to save the model and taper. We want to taper the cantilevers. The cantilevers in multi-pier begin at the center line of the pier cap. I'm at the center line of the column. Sorry, we'll go into overlay view. That'll help illustrate the point. So the cantilevers go from the center line of the column outward, and then same thing over here. Center line of the column outward. We have the length of the cantilevers already set. We set that to 10.5 feet earlier, so we're going to leave that alone. But now we're going to say, hey, we want taper. So I'm going to go ahead and click pier cap cantilever taper, check that box. Then we're going to go back into the suite of cross-section dialogues by clicking the enter button. And we're going to leave the cantilever base alone, because the cantilever base cross-section is right here. You can think of it as abutting up against the pier cap interior beam cross-section. So we want that to be the same, but what we want to modify is the dimensionality of the cantilever from the base out to the edge. And so to do that, we're going to go to the cantilever tip pier component, and we're going to modify the depth. So we don't want that depth to be as tall as the cantilever is at the base. Instead, we want to shorten it a little bit. So we're going to go from, instead of 72, make that 48. You can see that the rebar, the steel reinforcement, is now leaking beyond the boundaries of the cantilever tip. That's okay, because we just haven't got around to getting in there and modifying the steel reinforcement yet. So we're going to do that for the cantilever tip. Once again, edit section contents. We had used the percentage method before, where we were specifying a cover, and the program would generate a list of bar numbers and how many bars would be in the group for each bar number. But for this case, we're going to use the custom allocation method, which is going to permit us to input the actual starting coordinate in the 2 and 3 direction for each of the bar groups. So we have 4 bar groups. We want to keep the 4 bar groups, but we want to modify what the starting 2 and starting 3 coordinates are. We have a little drawing here to orient you as far as which way is 3, which way is 2, and then there's also a little orientation bitmap over here. So we're working on the cantilever, so you can see 2 is down and 3 is parallel to the ground. So we're going to modify bar group 1. We're going to modify its starting coordinate to a starting coordinate of negative 19 inches. And we're going to leave the starting 3 coordinate at negative 31 inches. And you can see it updated when after I input the 19, you can see that bar group 1 is no longer leaking beyond the border of the smaller cantilever tip cross section. It's now fitting within it. Good. We're going to now iterate, essentially. We'll select group 2 and do the same type of thing. We're going to modify the starting and ending coordinate, not starting and ending, but the starting coordinate in the 2 and the starting coordinate of the 3. So the starting coordinate for group 2 is also going to be negative 19. The starting coordinate of the 3, the starting 3 coordinate is 31. Okay, and our graphics updated. We'll go to group 3. And starting 2 coordinate is negative 19 inches. And then the starting 3 is negative 25.5. And you can see graphically that updated. And then finally, group 4, we're going to want to mimic, or mirror, I should say, group 3. So to do that, we're going to have a starting coordinate in the 2 of 19. And a starting coordinate in the 3 of negative 25.25. So now we have symmetry with regard to our bar group positioning in the tip. I click OK. I'm going to click OK. Okay. And now we can see that we can see the effects of that taper input where the cantilever tip is shorter or less deep than the cantilever is at the base. So we're getting close here. We're getting close. I'm going to go ahead and save the model. And the last major step that we have deals with the extra member. Okay, so the extra member page is the next page in the sequence of pages in the model data property sheet or property tree, I should say. So I'm going to click on extra members, and we're going to, before we position an element in the model that's going to be our extra member, we're going to first create a cross section that we're going to want to use in that extra element, in that extra member element. So to do that, I'm going to click the edit button, and that launches the extra member suite of cross-section dialogues. In the top left, you can see it's vacant right now because by default, there aren't any extra members in the default Pier model, but we're going to add one. So I'm going to click the add button, and that gave us a cross-section. You can see by default, it took the cross-section of our tapered cantilever. That's not the cross-section we're going to use, but it's applied as by default as convenience. We're going to modify, we do want rectangular, but we're going to modify the dimensions a bit. So we'll leave rectangular as the section type, but instead of 72 by 48, we want this to be 72 by 60. That widened it out a little bit. You can see the graphic update. And then we're going to come in and adjust the location of the steel reinforcement a bit. And this time we'll use the percentage method. So we're going to specify a cover in the 2 direction of 5 inches and a cover in the 3 direction of 5 inches and a minimum spacing of 0.1. We're going to click generate layout. And again, we'll choose our number 8 bar. And that's 40 bars. And now it's given us the bar group configuration, the steel reinforcement configuration that we want in our extra member cross section. So we've defined a cross section, but we haven't done anything with it yet. We haven't created an extra member element in the model that's going to use this cross section, but we're going to do that now. So I clicked OK, and zoom in a little bit here. I'm going to hide these loads. This isn't getting rid of the loads, but just for ease of looking at the model here and seeing the connection points for the extra member, I'm going to come into the context menu again. That's right clicking in the graphics window, and I'm going to choose nodal entities, and I'm going to uncheck loads. And that again, that didn't remove the loading from the model, but that hid it so that we don't have to look at it when we're choosing our node numbers. I'm going to right click again, and I'm going to select node numbering. And now we can see the numbers of every single node in the model. And that'll give us a nice reference point as per where this extra member needs to be positioned. So we're going to click the add button on the extra members page, and that's going to create an extra member element. And then we're going to supply, you can see the table just updated. There's now 1 data row for an extra member element. And we're going to supply the I node and J node values so that the cross section that we created moments ago will be used as the extra member cross section between the 2 nodes that we specify. So we're going to go for an I node of 2256. You can see it highlighted over here in the 3D as an indicator of the node that we just specified. And we want that guy to be horizontal. So 2217 is the J node. So I'm going to put in 2217. Okay, so we now have an extra member element from 2256 to 2257, and we want to use that cross section that we defined. So I'm going to choose from the drop down in the cross section cell, extra 1, custom. And now graphically it shows us a 2D image of what that cross section looks like. Okay, and I'm going to leave the end condition defaulted to fix. Okay, I'm going to right click and I'm going to look at this in thick view. Okay, and now we can see that the extra member is really nicely positioned at the base of the columns such that it's resting right flush with the pile cap, with the top edge of the pile cap. Give a minute, take a look at our model here. Okay, and I'm going to go ahead and save the model. Okay, so that's certainly by no means all the modeling capabilities of MultiPier with regard to the Pier model, but that we'll go back to the PowerPoint here. This is the model we just created on the right in MultiPier, and this is the model as it exists in the Melbourne Causeway. So you can see that's a pretty darn good match. We've got a little bit of time. Anand, you know what? I'm going to go ahead and I'll go ahead and put a little bit of load on the bearings just so we can, if you're okay with it, I'll go ahead and put a little load on the bearings.
Sure.
And then we can run an analysis and at least just take a brief look at a couple of the result side screens.
Yep.
Okay, awesome. Okay, so this is our model. We're going to go to the load page. And when I go to the load page, the interface is going to go into thin mode automatically to make it easier to access the nodes that we would want to apply loads to. So we can come in here and click on a node and then apply a magnitude in any of 6 degrees of freedom. I'm going to go ahead and load up each of these bearing nodes. There are 2 rows of 6. I'm going to go ahead and load up each of these guys with a 100 kip Z direction load. In fact, I'm actually going to go to the table here. Oh, I turned off, we're not seeing them. Because remember, I had turned off loads. There we go. So I'm going to make this a little easier. I mean, I could go ahead and click through here and just click on the nodes one at a time. But we'll go to the table. It'll be a little bit easier because the program creates placeholders for each of the bearings. So I'm going to go ahead and just copy the 100 and just dump it into the ZP direction for each of the bearings. How do I know these are bearings? Because the node type is specified in the node cell here. So this is bearing 1 in the left row, bearing 2 in the left row, bearing 3 in the left row, in load case 1, load case 1, load case 1. And we'll just do one load case for this model. So I'm going to go ahead and finish out each of the bearings. And great. Okay, cool. We've got a 100 kip load on each of those. I'm going to click OK. And we can take a real quick look in the 3D view. There's our loading. And let's save the model. And I'm going to go ahead and run an analysis. And we'll take a look at a couple of the result side screens. This demonstration was mainly about the edit side of the program, but I guess I must have flown through the slides because we actually have a little bit of time. I didn't end late for once. So that's our analysis that we just ran, and we got convergence. I'm going to go, these toolbar buttons to the right of the analysis lightning bolt are your entry points to the different result side views. So we're going to jump right to the 3D results. So if I click the 3D results toolbar button, what we get is a drawing by default that's showing both the undisplaced model, which is the top one, and the displaced model, which is the bottom one. And we see the loads there as well. See, everything is as we would expect due to the 100 kip loads in the ZP direction. Everything's getting pushed down a little bit. For clarity, you might want to come in here and say, hey, I just want to see the displaced model, right? So now I turned off the undisplaced model. You can look at the amounts of displacements and rotations as calculated by the analysis by clicking nodes in the 3D view, and the corresponding data, the displacements and rotations, will display in this window to the left. So as I click through nodes here, we can see you're getting feedback regarding what the displacements are. Let's see, let's take a look at, we'll go to pile results also. This is our plan view on the results side, which looks very similar to the edit side. And in this view, we can see force plots as well as displacement plots and soil force plots for whichever piles we select. So we'll go ahead and use the drag box option again. That's from the context menu. I'm just right clicking and I'm going to choose select piles, drag box. And that's going to allow me to select a bunch of piles instead of having to like pick each one, this one and this one, this one. I can just drag box it. So I'm going to be like, all right, let's take a look at these 6 piles right here. And when I did that, the 6 piles highlighted because I just selected them. And then the plots for each of those piles, draw down in whichever of the member force or pile displacement or soil force windows are checked. So in this case, we've got the moment 3 and 2, axial and DC. Those are our selected member forces. And so those are the plots that are showing for those piles we just selected. If we want to see shears also, I can click the 2 shear checkboxes. I can click redraw curves. And now we've got the shear 2 and the shear 3 also. We have a feature that allows you to view the specific points that each curve is comprised of. And that is accessed by clicking in the plot window of interest, right-clicking, and then clicking printable graph. So when I do that, I get a dialog that has a reporting of all the piles with the color that we're using to draw them up here based on their selection, and the shear, in this case, the shear 3, along the length of the pile. So these are the corresponding node numbers, and these are the shear 3 values along the length of the pile for the currently selected load case. We have load case 1 selected right here. If we selected load case 2, then this dialog, when we launch it, would show load case 2's values for the selected piles. If we scroll to the right, we can see that the way this table is set up, it's chunks of 4 columns. So here we have pile 4, and it's 4 columns worth of data, that being its node numbers, the elevation of each of those nodes, the shear 3 at the I node, the shear 3 at the J node. If we scroll a little bit farther to the right, we get another set of 4 columns, which is for pile 5 for load case 1, its shear 3 values for its nodes at those specific elevations, its shear 3 and its shear 3 at the I and shear 3 at the J node. Let's see, let's take a look at interaction diagrams. We'll take a quick look at that. I think we're going to move the legend here. Depending on the interaction diagram, the legend in the bottom right can get covered up, just depending on the way the interaction diagram is drawn, but you can move the legend position. So we'll move it up to the top right, and that's less invasive, a little easier on the eye. So with the interaction diagrams, which again, I got to by clicking on one of these toolbar buttons. In this case, it was this one with a mouse hover. We see that's the column cap connection. I'm going to zoom in, and we can click on in the Pier element selection window. We can right click to launch the context menu, select element selection, and then I can come over here and I can click on an element and see a reporting of data for that element. So the DC ratio at the I and J node for that's 0.07. That's element 33. The axial values are this, the moments are this, and I can click through here. And as I do that, you can see that the values are updating as per the element that I'm selecting. I selected that extra member. Recall we have 1 extra member in our model, so I just selected that. And here's the reporting of the data for the extra member element. Let's see. We also have a report generator, which is a really great way to view results data. It lets you be very custom. Operating system denied access to specified file. Okay, maybe I don't have the latest. Sorry, maybe I don't have the latest XML report generator on my machine, or maybe I forgot to select XML. No, okay. I may not have. Sorry, folks. I may not have the XML report generator that's compatible with the version of MultiPier that I'm using right now, which is the latest released version, which is 6.2.1. It is a good feature, trust me. Let's see. Okay, I think that's
show
pretty
it
good.
if you
yeah, if you want to. I feel like it's a good feature. I don't know. It's a very targeted way of viewing a lot of results data, so I think it's super handy.
So let me know if you can see, Clint.
Yeah, I can see your screen. Do you want me to move MultiPier off and you just take over the screen share?
I think I have the screen share on.
Oh, okay, good. Oh, yeah, you do. Okay, great.
So after we click on the result, your XML generator, you have options here. You can select all or be more selective. That's the main idea of the XML report generator here, is to cherry pick whatever data you want, and then click generate. and that will create your report here with nice screenshot of your cross section. This is the input side, and then also if you go down, there are result printed as well. So max and min, Pier column, Pier cap strings. So if you want to get that, we have, these are the forces that Clint went through in the pile result window. We went through axial, shear. So the same thing here through the depth of every pile. So it will really be handy for like creating a report for exactly what input parameters you have entered and the results you got.
We can probably jump into the Q&A, Anand, if you want to.
Yeah, so if anybody has any questions, please raise your hand and we'll unmute you.
Actually, Anand, there's a good question that might be good to answer live from Bowen Yang in the Q&A panel.
Sure, yeah.
You want to take a look at that one? He's asking about if you have a long bent cap and need to input transverse shrinkage loads, how could we do that in the FB-MultiPier model? And also if they have a bent cap that is like, it's got a small 3-inch gap and they only want to model half of the cap with half of the bearings, how should they adjust the wind loads to reflect the actual wind load on half of the bearings? So it sounds like they want to model like only half of the model, and so how do they account for that pretty much? Do you have any input on that, Anand?
First of all, like the transverse shrinkage loading, you can manually apply like the load on the cap in the transverse direction on the cap that would provide you the shrinkage. So if you have shrinkage load, you can on the first node and the last node, you can provide that load and that would get you your shrinkage. If you have a bridge model, we do have the temperature loading on the span itself. So in there, you can actually provide the temperature differences, and the program will calculate the compression and tension depending on if you're reducing the change of temperature is less or more, right? If it's heat, is it hotter or getting colder? So depending on that, the program will apply the compression or tension on that span. But for the bent cap itself, you have to apply your own load to get that effect. 3-inch gap, we can model only half of the cap. So I have to look into that. So you want to delete one of the cap element you're saying, and there are 2 of them. There are a few nuances to like, I want to make sure I don't.
Hi.
Hi.
Can you hear me?
Yes, I can hear you.
All right, thanks. Great presentation. I just have a quick question, like, cause we got like a long band cap, and we got like 3-inch gap at the middle, pretty at the middle, and we want to model only half of the band cap. So considering like the bearings, right? So we got maybe just model half of the bearings in the model, and when we do the wind load generator, like, because it seems like it's assumed like it's a whole bridge, but actually we only model the half of the bridge. So I think the wind calculation off a little bit. So we want to know that how do we adjust the wind load input so to truly reflect that it's just only half of the model, half of the bridge was model, is not like whole bridge was model.
Okay, so let me open up a bridge model here. So for bridge model, you're using AASHTO. And in AASHTO, you're using the wind load generator. This is what I'm thinking you're using, right?
Correct.
And then I have all Pier here, so I have to use the bent Okay, so I can use the bend in there, and you're saying when you do that, so if I go to the bridge, place the first pier with a bend. So if I do that, yeah, I'm just gonna scoop few things up, which is fine. We just want to check the wind load generator. Okay, so for the bend, you can actually provide your own transverse area. So if you just provide half of the transverse area of your bend, right? And then what will be the moment arm for that? And same with this is for the superstructure, but on the substructure, which is your pile bend, you can provide your own half of the bend dimensions only here, and the program will calculate the area of that half of your bend dimension, and then calculate the wind, so the wind pressure for that, and then apply it on those half of the bearings you're only provided, right? So even if you have actual, you provided an actual dimension of your whole bend, you can actually, on this, you can just provide the half of the bend dimensions only. That would just capture that area and the pressure and apply it to just your half of the wind, half of your bearings.
Okay, I think the question, maybe I need to rephrase that more clear. So if you so we got half of the bearings. Actually, I'm thinking about the overturning wing loads. If you see this diagram, like for the wind load generator, like for example, the right side of the bearing is actually go down, right? If you consider the wind from left to right.
Yeah.
And since we only model the half of that, like we got the right side, the bearing is a go down, but actually in reality it should go up because it's a whole transverse, like transversely is a long pile, long band cap, but we only model half of that. So that's probably my question right now is how to crack the right side of the bearing direction or the wing loads right now. Yeah.
Let's do like a deep dive. I'll get back to
Yeah.
you, and then we can
Perfect.
talk about your specific case. And I think with like few minutes here, it will be very hard for me to go through that. But let's follow up on this sometime this week or next week, and we can go over your
S-
specific
Sounds
case.
good. Sounds good. Thanks
Awesome.
so much. Yep.
So really quickly going over the other, someone had message. I think we answered that. The last one. And then I think the only open question I have is from Morales. Can the pier cap taper be modeled distance from the center of the column? Unfortunately, no, at this moment. But just to let you know, but there is a workaround for that. So you can create your own sections in the program as you've seen using extra members, right? So if you just use the regular cantilever, or just use the cantilever, when you provide the detail for cantilever, provide it very weak cantilever properties. That way the actual cantilever is not getting used by the program. But you do have the elements and the nodes in the cantilever. So you select your different sections of your extra members, and then apply those extra members on your cantilever, one element at a time. And that way you have more control over how your taper look, where it starts, where it ends, and how it looks. If you want, like we can demonstrate you that later, one-on-one, if you prefer that. But I think with the time I have, I think that hopefully that will make sense to you. Another question here is, how do you typically handle thermal deformation in the cap? Can the expansion and contraction of the pier cap be modeled? That's a good question. For bend, I already told you, like, we don't have any inbuilt generation of forces in the cap. So you have to apply those loads on the bend cap. because the bend cap is an element, then it stays like that. For Pier cap, which you have a shell element, there is no like, unfortunately, we don't have an inbuilt way of getting that thermal deformation in. But that would be a nice add-on. Like if it is need, if you guys are using that, I think I have another question that somebody asked about the same thing. So definitely we will look into like adding that option where depending on your temperature and all the other components, we can generate the loads for you and apply it on the edges or in the within the cap nodes. But unfortunately, at this moment, we do not have that feature. I think we are all out, like we have 1 minute over. So I just wanted to quickly wrap up. So we always welcome for suggestions, like email us, like if you have any specific thing you want to see in the webinar, advanced topics, vessel collision or fender model or anything like that. We do have another 2 webinars coming up. As I've showed you that, please register for them. And I would definitely follow up with some of your questions that we did not get time to go over completely. We will be sending the CE credits to you, credit certificates to you guys who has provided the PE numbers to us. So hope this was a very valuable experience seeing this webinar, and please reach out to us with any suggestions. So that would be it. Let's conclude the webinar now. Thanks.
Thanks, everyone.
Thanks. Have a great day.